So we looked at an easier net force problem, but we can have a similar problem that's just a bit more complicated. So once again, we'll assume that we have a sign that we're hanging from the ceiling. But this time, for whatever reason, we decided that we wanted to have a wire connecting the two strings that are holding up the sign. And we'll add a certain symmetry. We'll say that these two angles are theta, and the two angles on the right are phi. And so now we can label these T1, T2, T3, and T4. And then in the middle, T5. Okay? And, so once again, we want to find all the tensions in the wires. Okay? So how would we solve one like this? Well, we're going to do this in stages. So you've probably noticed by now with a lot of problems we have that, there's some problems that are simple that you can solve by just setting up one equation or maybe one system of equations and solving it. And other times you have to divide it up into steps. For a lot of the collision problems, it meant that we had one step when we were using conservation of energy, then we had a step when we used conservation of momentum, and then we had a step where we used conservation of energy again. Or some combination of those different ideas. Sometimes we would have work that would have to be thrown in. So this is kind of the same way, but we don't have things happening at different times. We're just going to be looking at different places. So the first thing we'll do is we'll look at the sign. And so we'll sum all of the forces that we can find on the sign. So the force on the sign, well, we have gravity. We also have a component due to T1. We have a T1 cosine theta and a T1 sine theta. And then we have a force due to T4. We have a minus T4 cosine phi and a T4 sine phi. And so you'll notice here that if we look at the forces on the sign, this is exactly like the problem we saw before. Just with different numbers. But this is solved in exactly the same way. So I'll go through it quickly now because we just saw this in the last unit. So we would say that T1 is equal to T4 times cosine phi over cosine theta, and that tells us that T4 times so T4 times cosine phi tangent theta plus sine phi is equal to mg. So we have T4 is mg over cosine phi tan theta plus sine phi, and T1, I don't even have to plug this in anymore because we remember last time we saw due to symmetry, I know this is just going to be cosine theta tan phi plus sine theta. And if you want, you can pause the video and go and do this on your own and show that you get this result. Okay, so now we found T1 and we found T4. So now we need to find T2 and T3. So what I've seen some people try and do who have already taken this exam is they just count T5 as a single force and T2 and T3 as single forces. But if you do that, you're not going to be able to get the right answer for a problem like this. So instead what we have to do is we have to say, let's call this point right here P125, because from here we have a T1 going down, a T2 going up, and a T5 going to the right. Okay, so if we look at P125, we see that we have F125 is going to be equal to, so we do the forces again. So we look at all the forces on this point here. So we have a minus T1 cosine theta and a minus T1 sine theta, because again, we're going down and to the left, plus a minus T2 cosine theta and a positive T2 sine theta, plus we have a positive T5 and 0. So now if we look at our y equation, we see that the y components of T1 and 2 we have to balance. They're both multiplied by a sine theta, so we see that in this case T1 is equal to T2. And so then we can just plug this in here into the next equation, because remember this is equal to 0, and I should have said that for this one up here, of course. And so this means if T1 is equal to T2, then 2T1 cosine theta is equal to T5. So now we found T1, T2, T5. The only thing we need to find is T3. And so as you can imagine, we're going to call this point P3, 4, 5. And if we look at P3, 4, 5, we see that F3, 4, 5. So the force from 3 is here. We're going up and to the right. So this is going to be T3 cosine phi, T3 sine phi. We have T4 going down and to the right. So T4 is going to be a T4 cosine phi, and then a minus T4 sine phi. And then in this case, we have T5 is going to the left. So we have a minus T5, 0 for x component. So again, looking at the y components, we see that T3 is equal to T4. And then we see that T5 again is equal to T3 or T4 cosine phi. And so then this even gives us a relationship. If we had wanted to solve for, if we'd only been given one of these angles, we see that we could still solve it using this equation here, because T5 is equal to each other. And so this would even, we could have only been given a single one of these angles, and we could find what the other angle is by using this. So, well, maybe we couldn't. It may be a little bit more complicated because these are all contained mixes of angles. But it would be an interesting problem to work out. So there you have it. We've solved for all the tensions. And you can see it was, we'd had to do this in several different stages. But we also see that we had a symmetry in this problem again. And that's because we had the two angles on the left be the same, the two angles on the right be the same. And so, the top and bottom tensions were the same on each side. And, and again, I think in most of the problems that you do involved in statics, you're going to see some types of symmetry that come out. And so if you get an answer and you see a symmetry like that, it doesn't mean that you have the right answer. Just like having the correct units doesn't necessarily mean you have the right answer. But it's a good check. Because if you have that, then you can feel a little bit more confident that you're probably going down the right path.